Good evening and welcome, friends. Can you hear me properly? Can you let me know on the chat? Friends, my name is Anshumala Gupta, and I'm from the Joy of Learning Foundation, Delhi-based. And I have one colleague here, Manisha. Manisha, will you say hello to everyone?
Hello, good evening, everyone. Myself, Manisha.
And most of you are probably new to our session, so a very warm welcome. You will see that in our sessions, we not only explain concepts, there is always an embedded pedagogy which you can use in your classrooms. So that also we'll present, and that's why we'll go slowly. And secondly, I want to underline that mole concept is something which most students are terrified of because it's a very large number, and actually they don't know why or from where it has come and why it's important. So it's important, and it's a very vital concept for chemistry, very important. So we should understand it thoroughly and also from where it came. So let me begin. Uh, yeah, so I'll just share my PPT. So give me a minute. Uh, so suppose, friends, we are deliberately giving you a simple thought exercise. Let's suppose you had to make a recipe and which had ingredients A, B, C, and suppose you had to somehow ensure that you in that recipe A, B, and C will be equal number of particles, not weights but particles. And the recipe of the medicine has to be prepared in kilos, which means quantities are large. So what will you do? I mean, if you have to make equal number of particles, what will you do? Friends, you can write on the chat. You can, of course, speak and say, but I mean, chat box is, through chat box, we'll be doing most of the conversation. So what will you do if you have to like have large quantities, but then you have to ensure that the A, B, C are having equal number of particles? What can you do? Small particles. Nilofer is saying Vhe. Nilofer, please elaborate a little. Vhe what?
मैम हम ये वे करके देख लेंगे कि कितने किलो में कितने पार्टिकल्स आ रहे हैं और उस हिसाब से हम नंबर ऑफ पार्टिकल्स ले लेंगे उसके अकॉर्डिंगली.
So you will count the particles in each kilo?
Yes,
Somebody
ma'am.
said we'll take larger, but that would be very hard because think of it, particles are very tiny. I mean, suppose you have particles like these. So if
Okay.
you start counting in 1 kilo, you will go crazy. So
तो हम कम क्वांटिटी कर लेते हैं मैम, ग्राम में देख लेंगे, मिलीग्राम में कर लेंगे, जो हमारे लिए काउंट करना इजी हो जाए. देन वी विल मल्टीप्लाई.
so what will you weigh first? Suppose these are your three ingredients A, B, C. So what will you weigh?
Ma'am, weigh of one particle
Right.
and then weigh of 1 kilo particles and then divided by, then we will get the number of particles which will be there in 1 kilo.
So you are saying that you are going to count particles in 1 kg?
No. Ma'am, we will weigh the number, we will weigh 1 kg and we will weigh the size of mass of one particle. So
Okay.
when you divide, you will get the number of particles.
All right, but now you have to ensure that you have to have equal number of each of these. So then what will you do? Yeah, so see, obviously everyone's saying we'll weigh one particle, and then one person is saying follow the way of counting nanoparticles. So see, suppose I weigh one particle of pea, one particle of this dal or pulse, and one particle of rajma. Now, what is the next thing should I do? I have to combine equal quantities of each of these, equal numbers.
Ma'am, we have to, I mean, suppose one particle is say 1 gram, and one kidney bee particle is say for 2 grams.
Okay.
So I have to take, I mean, that many peas that it should weigh 2 gram, and then that many pulses. I think this is whatever pulse it is. So that should be equal to 2 gram. So then I can have the number of particles.
Okay. I mean, you are constantly equating weight.
Yes.
And what you need to equate is number of particles. See, the problem here is you have to have the counts identical, not the weights identical. And each single particle is of different weights. So you have to make equal counts. And the count is pretty large. I mean, you can't individually keep counting one by one. You will go crazy. I mean, think of counting peas or counting rajmas and all that. So the counts have to be same. The numbers have to be same. So how do you ensure equal numbers without actually counting? That's my question. So of course, many people said they will weigh one particle each. All right, we weighed. Now what do you do? After you have a weight of this one, suppose 1 gram, this one 2 gram, this one half gram, whatever. Then after that, after weighing, what do you do? Yeah, everyone is saying weigh one particle. Correct. We can weigh one particle. But after that, what do I do? Take the needed ratio. Ratio of what? Ratio of weights? I mean, this one person is saying who's RA211. So ratio in weights, are you saying should we take them in required ratio of weights? Ratio of what? Any answer? Ratio, I mean, suppose we take ratio of what? And if we have weighed one particle, total weight of beans divided by one bean. But we don't have any total weight of beans. See, we have to take the weight of beans required. You have weighed one bean. Now what? So Syed Ahmed, what do you say?
Excuse me, ma'am. Good
Yes.
evening, ma'am.
Yes.
Ma'am, actually, rajma means it is sizes bigger, maybe the weight also bigger also, and just same for green peas also. So when we are weighing means when you are saying taking single piece, the rajma may weight higher. So altogether we need 1 kilo means we'll have to take more number of this middle one yellow dal and the less numbers of rajma. So we will first we'll take the weight. Accordingly, we can go with the ratio.
Yeah, so my question is, I mean, you are moving towards that answer, but not giving me the full answer. I'm saying that, okay, I never said that it has to be, total has to be 1 kilo or anything. I said the number is large. That's all. The number is large. So you can't, I mean, you can't take like You can't count actually. You can't count 10 of this or 10 of this or 10 of that, and the number is in thousands or tens of thousands. So you can't count, but you have to somehow ensure that they have equal numbers of particles. So Firdaus and this person who's named himself or herself Mole is saying, my concern is that each thing are different in size and shape. Then how is it possible to say that each things are 1 mole? I never said 1 mole. For example, I haven't even used the word mole. 1 bowl rajma, 1 bowl dal, and 1 bowl peas. Okay, so this person, the person who's giving an answer, he's saying we should take 1 bowl each of the 3. So 1 bowl each means taking equal volume. So if you take equal volume, will you get equal number of particles? Firdaus is saying we'll weigh all the 3 separately, ensuring that each weigh contains same number of particles. See, so if you're saying each weight contains same number of particles, that means you are counting particles. I said you can't count. There are too many. There are thousands and thousands. You will go crazy counting them. That's the problem. The problem statement is this, that you have a very large number of particles. So you can't count. You can only weigh. I mean, you can weigh 1 particle. That's possible. And now you have to mix the 3 in such a way so that equal number of particles of peas and rajma and dal is there. So what do you do? So Syed Ahmed is saying taking number of particles as X. Yes. And then what will you do?
Ma'am, actually, I think we have to compare their way of each particle.
Yeah.
And then, for example, if 1 particle of okay, I mean, we have to first do the comparison of their weight, like in 1 gram,
Okay.
say 4.
Okay, I'm just giving you weights of these. We actually weighed them just to give you an idea. So 1 particle of A is 0.2 grams, 1 particle of B is 0.04 grams, and 1 particle of C is 0.29 grams. Now I have weighed them. Now what do I do? So Al-Saba is saying that we take the ratio of weight of 1 divided by total weight. So she says that we will find weight ratios. So Atharv is also saying we have to find the ratios. Yes, you can do that. Definitely you can do that. Actually, essentially, if you have the correct ratio of weights, so that the particles come, then if you take that correct ratio, then particles will be in the same numbers. So that will give us equal number of particles. You are right. Actually, you're thinking very mathematically, but one simple solution could be that you just multiply this number. I mean, suppose you've got 0.2, 0.04, and 0.29, you just multiply each with 1000. So if you multiply each with 1000, what you get is 200 grams of A, 0.20 gram into 1000, 200 grams, and this also 40 grams, and this gets 290 grams. You can multiply by 1000, you can multiply by 10,000, you can multiply by 100,000. You can take a sufficiently large number and multiply so that you get their weight in suitable units, convenient units. So, here I've taken 1000, but you can take 10,000 also. If you take 10,000, it automatically becomes 2 kilo. So, which means that you get weight ratios just by multiplying with a large number. So the method that you were saying is correct, but we don't even have to do that much trouble, take that much trouble. Simply multiply with this with a large number, all 3 of them, with the same number, right? And we get these 3 weights. So, and if we take these 3 weights, we have equal number of particles in the recipe, right? Simple. So which I have shown, suppose we take that in your recipe, so much of each, then you have equal number of particles in your recipe. Now, suppose the particles were very, very small, even smaller, and their numbers were very, very large. Still, you can use the same strategy, except that multiply with a very, very large number. I mean, 1,000 will not do. You may need to multiply by 10,000 or 1 lakh or 10 lakh or whatever. I mean, you want the weight in some desired number of grams or kgs so that it's convenient. It's a convenient weight, right? So that's what we are going to do. Suppose these are our particles. So which means, I mean, you are probably, many of you are chemists. Do you recognize what this is?
Copper sulfate.
Yes.
Copper sulfate.
Yes.
Copper
So
sulfate.
suppose, yes, correct. So suppose we have copper sulfate with us and we have, suppose, iron powder. Both have very tiny particles. And we know that suppose we, I mean, if we make them go through a chemical reaction, we'll need to dissolve the copper sulfate. So it makes a solution like this. And if we, yeah, it's hydrated copper sulfate, correct. So, but currently for the reaction, we need to dissolve it in water and then put iron powder in it. So when we do this, we get these two products. The products is ferrous sulfate, which is like light green in color, and then we have brown copper. These are the two products. So I have to what I want to do is like combine copper sulfate and iron to give me ferrous sulfate and copper. Now the question for me is, what quantities of the reactant? Yeah, sorry.
बस मीटिंग में ट्रेनिंग मीटिंग चलायो हाँ
Please, there's some yeah, so suppose I have to take my two reactants so that I get the maximum amount of products. I mean, my reactants react fully, combine fully, and give me maximum number of products. How much of each reactant should I take? What will be a good idea? What do you think? So how much of copper sulfate and iron should I take? So the person who is RA, he said 1 mole. But where did this 1 mole come from? I mean, of course, you have heard this in chemistry. Chemistry tells you immediately that combine equal moles. But how did we reach this conclusion? Any idea? Why should taking in moles of each make it better? So one answer is, considering each thing, they are weighing different as their sizes are different really. Then how can we calculate their weight uniformly or say it as approximately? We are not calculating their weight uniformly. We are simply weighing each particle earlier. And I mean, are you talking the person who's written mole? I mean, are you talking about the previous thought exercise we were doing with peas and rajma, or you were talking about this one?
This one, ma'am.
This one. Okay, okay. Yeah. So, okay, Veena Suri is saying molecular weight ratio. So, but, so which is the mole? But my question is, why are you taking the mole? What is the logic? Why should we take equal moles of each? Can anyone tell me?
They contain same number of particles.
Okay. So Firdaus Bhatt is saying they contain the same number of particles. Yeah, you are actually right. But what I'll do is I will take it through, you know, a journey where I do not assume that, right? I do not assume that what is 1 mole and how a mole is. Firdaus is saying fixed standard, but the question I'm raising is, where did this fixed standard come from? So Neelam Verma is saying equal quantity of both. So equal in terms of weight, equal in terms of volume, equal in terms of what? If I want to take equal amount of both reactants, it should be equal in what? Mass. Okay. So Atharv is saying mass. So one possibility is that we take equal in mass or we take equal in volume. Which would be better?
Mass.
Some people are saying mass, but let's see. So we will actually do this.
Ma'am, one question. If we consider each particle of iron powder or copper sulfate, taking as one minute particle,
Yes.
each one is weighing differently. That is my
Correct.
question. Then
Yes,
how
yes.
can we say that it is in equal in mass?
Right. So when we are taking, see, we are taking like these two powders. So some people are saying, for example, Atharv and another person is saying, suppose we take 1 gram of each, or we take 10 grams of each. So I mean, the number of particles inside may or may not be same, but they're saying like if suppose particles is something we cannot look at, so maybe we can take equal mass or we can take equal
But
volume.
there is a contradiction in that, because if we weigh 1 gram of iron powder, it contain different types of minute iron particle,
Right.
and weighing differently. Each one we take and weigh, it is different.
Absolutely.
Then
So-
how can we say that it is in equal in mass, total?
No.
That is my concern.
We are not saying they are equal in mass. We are taking equal masses. See, we are doing the experiment
Yes.
by taking equal masses of both the reactants. See, we can take something equal of both reactants. What we want to see is what happens if I take equal masses of both copper sulfate and iron. If I take equal volumes of both of each of these. So actually, I mean, usually in a face-to-face workshop, we actually do this. But right now, I'm only going to show you a video.
My concern is that how can we say that it is equal? On what ground we say that it is equal?
We are taking it equal. We are taking 10, suppose we are taking 1 gram of each. So it's equal because we have weighed it
But
equal.
that 1 gram of each particle is different. That particle contained in there, it is entirely different from another.
Correct. That's correct. You are right. See, you are right because you understand it. You are looking at it from a chemist's point of view. But suppose if you ask your children, if you ask your class, how should I mix copper sulfate and iron? So they will say either equal mass or they'll say equal volume. Right? They'll say take equally. Then when you ask equally what, then they'll say maybe equal mass, take an equal weight of each. See, if I had not...
But if a student asks questions like me that I told you, then how I can answer it?
So my question to you would be, I mean, suppose you are the student, my question to you would be, okay, so let me not take masses, let me not take volumes. What should I take then? That's my question. And look, you are not a chemist, you are a student, you are a child who doesn't know anything more. So you have to give me, so you are my student, I'm asking, so what should I take? You are saying don't take equal weights. Okay, I'll not take equal weights. I'll not take equal volumes. Then what should I take?
I am asking is that chemistry is varying differently in different times. Their theories and different inferences and different viewpoints. Then mole is always a headache to everyone.
Yeah, because... so will you give me a chance to please establish it?
Okay, thank you.
Yeah, I have a 2-hour session. I have not answered any question so far. But please give me a chance to proceed. And mole is a big headache for everyone. And today I'm going to show you where it comes from. It's a very simple idea, very simple and a very elegant idea. But we should at least... So the only question I'm currently asking is, I have 2 reactants.
Okay, you can proceed. You can proceed. I am not interfering. My concern, I am asking my concern. That is all.
Yeah. So the thing is, say, it's like we are having 2 reactants, and I am asking you as a group, or I would ask a group of children also, that what should I take? I mean, if I want that my reaction should proceed well, So how much of each should I take? So typically anybody will say take equal. So equal means what? Equal masses. I mean, because we can only weigh. So should we take equal masses or should we take equal volumes? Yes. Yes, please.
To get to get the desired product, I think we should take the equal quantity as in equal number of the each reactant. Since I know the term reactant, so I'm using reactant. So
yeah, so you were saying take equal number of particles?
correct. Yeah, right.
Yeah, so see, that's something very that's something you know as a chemist, but children don't know, right? Children
So
don't know that. And
I agree.
also, and secondly, how can you even count particles? How will you count number of atoms? You can't. Number of atoms or molecules, you can't. So you have to have some method, right? I mean, see, it's like the only thing you can physically, in a real sense, measure is either weight or volume, right?
Right. But you just before you mentioned about a little bit about quantity, the number of particles when you took the examples of bees, the pulses, and then that gram, the beans. So on the basis of that, maybe children might be able to answer about it.
But anyway, don't worry, we'll come to that. I'll use that example. I've not used it as yet. I'm simply asking you how much of each reactant should I take? See, I'm just proceeding, right? I mean, like I've not finished anything nor initiated anything.
We can write the reaction, and since in this particular one atom of iron is reacting with one molecule of copper sulfate, so hence the weight of one atom will react with weight of one molecule. So this is how we can see how much weight of iron to be taken and how much weight of copper sulfate to be taken.
Right. See, you are actually proceeding in the right direction. But what if I ask you? I mean, if you take atomic and molecular weights, this is precisely what I'm going to do. But then after that, you know only atomic weights. What will be the real weight you will take? I mean, in real life, you don't have atomic weights. You have grams and kilograms. So what will be the actual weight you will take? And there it gets into a difficulty. What do I do? We don't have atomic weights in front of us, right?
Atomic weight, we'll take gram atomic weight and gram molecular weight in that.
So I'm asking, where did that come from?
Yeah.
Gram atomic weight. Somebody told you use gram atomic weight, so you're using it, which you call the mole. I'm asking, how does it come? And that's precisely what I'm trying to show. So actually, I mean, if since we have done this, I want to show you this reaction in which we have taken both of these in equal weights and equal volumes. I just want to share it with you. Let me just give me a little time. So मनीषा, तू दिखा सकते है क्या? तूने खोला हुआ है क्या? नहीं तो मैं खोल रही हूँ.
हाँ, मतलब स्क्रीन पर वो है 0.5 समथिंग, मतलब पिक्चर है या वीडियो प्ले करूँ?
अच्छा, नहीं, मैंने वीडियो कर रखा था फिक्स, तो मैं अभी दिखा देती हूँ वीडियो. या उस वीडियो में इट्स लाइक at 9:34 minutes. तो विल यू शो? नहीं तो मैं भी दिखा सकती हूँ.
1 minute.
So 9 नहीं, वो वाले में, the webinar video, not this one. चलो मैं दिखा देती हूँ. Give me a second.
स्क्रीन दिखाई नहीं.
हाँ, एक मिनट, वो मेरे को तो see here we have taken this, we did in a webinar. We have taken equal weights of copper sulfate and iron powder, like measured them properly. So for equal weights, we took a gram of each, and here for equal volumes, we took a small spatula of each. And then actually my colleague did this experiment. So we actually, dissolved it. We had to heat it a little also. And then on these test tubes, we actually wrote V for equal volumes and W for equal weights. And then we will show you the results. So results are here on the screen. So you see, we have deliberately chosen this experiment. It's very, very nice because here the reactant has a very bright blue color, but the product has a greenish color. Firstly, the ferrous sulfate is greenish in color. So from color change, you can actually assess how much it has changed. So one is that. Two is iron powder is black, whereas copper powder is brown. So you can even judge from color of the products. And the third thing is any remaining iron powder can be tested with the help of a magnet, which my colleague is doing here. So I'll show you. She actually is using a magnet to see how much iron powder is left. And what happens is that in both these cases, when you take equal volumes of both reactants and you take equal weights, there is quite a lot of reactant remaining. There's iron powder left, and also the color of copper sulfate doesn't change completely to ferrous sulfate. So the reaction actually doesn't get to completion or doesn't happen well. So Firdaus is saying, respected participants, please behave like students. Yes, sort of. I am putting you in the shoes of students, children who don't know all of chemistry, who don't know mole, and for them you are asking, okay, I have these two reactants, how much should I mix? And they'll say equal weight or equal volume. So we did both, and we did not get a good result. But now if we want to reach the mole, what do we do? So I'm going to do. And I'm going to proceed further. So I have to close this. Wait. So when we took equal volumes and equal weights, we did not have good results. So now the question is, what should we do so that the maximum of this gets converted to maximum of that? I mean, like we get the best results. So when I'm asking you for suggestions, I'm not asking for your suggestions as chemists. Because as chemists, you will say the mole. But if we ask children, they won't have very many suggestions. They won't know really. So let's start with the chemical reaction, as one of you had actually suggested. So we write the chemical reaction here, the equation. Now, does the equation tell us anything about quantities? What does this equation tell us about quantities?
They know about the balance reaction. So each one atom like that it will be, because they are having not much number.
Correct. Yes. So one atom of iron, yes, correct. One atom of iron is combining with one molecule of copper sulfate to give one molecule of ferrous sulfate and one atom of copper. So we know this in number of atoms and molecules. Does it tell us anything about weights?
No, ma'am.
Can anyone say, does the equation tell us anything about the weights?
Ma'am, according to the law of conservation of mass, we will know that, okay, if we take 1 gram of iron and 1 gram of copper sulfate, then on the other side of the reaction also we should get a total of maximum 2 grams, right? So based on that.
Okay, correct. We know that weight will be conserved on both sides. Any other information the equation is giving us about weight of reactants or weight of products?
So a student might actually say that an atom of iron has this atomic weight, or the molecular weight of copper sulfate might be so much, and I just have one molecule of copper sulfate, so that is the weight.
Yes, exactly. So we know the atomic weights. So because we have one atom combining with one molecule, so let's okay. So I mean, here we are now getting into the same thing which we did with those peas and rajmas, that we had one particle each we had weighed, and we multiplied with a very, very large number. So that's the same thing we can do with this equation also. So the masses of particles here are what you said, atomic masses, written in atomic mass unit, AMU, or which is also called, somebody is speaking, please mute your mic, otherwise it disturbs. So atomic masses are written in AMU, or also U, which is unified atomic mass. And so let's write these, and we know that AMU is 1.66 into 10 power minus 24 grams. So, and it's also equivalent to one hydrogen atom, mass of one hydrogen atom, or mass of a proton or a neutron. That's how we define it. So, and usually we don't write the unit, we just say in comparison to hydrogen. We write in relative atomic masses. So hydrogen we take as 1, and then we say carbon is 12, oxygen is 16, sodium is 23, chlorine is 35.5, because this is like, it's taken an average of isotopes. So here let's write this in atomic masses. So these are the atomic masses of various elements involved in this reaction. So, if we put atomic masses of each of these in the equation, so then we get this. We get that 56 U is used for atomic mass, 56 U of iron, and 159.5 U of copper sulfate gives us 152 U of ferrous sulfate and 63.5 U of copper. So we have the whole equation now written in atomic masses. Now, what we did with our earlier particle exercise, where we were talking about peas and rajma and all that, all we need to do is find a sufficiently large number, a good number, with which we can multiply this. This is a very, 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 very tiny mass. So if we have a good number, we can multiply all this with that number. So we can take so many, a big number of iron particles, a big number of molecules of copper sulfate molecules, and then our reaction would proceed equally. So we actually need a good number, a number to multiply all these with. How many particles of iron, or rather how many atoms of iron and how many molecules of copper sulfate, we need that. We know their individual weights, weight of one particle. So, and of course, we need to measure in actual grams. So we need an appropriate number. So what we do is, we know that 1 U is equivalent to 1.66 into 10 power minus 24 grams. So 1 U is this, 1.66 into 10 to the minus 24 grams. If you just write it differently, 1 gram is 1 upon 1.66 into 10 to the power minus 24 U, which is, so 1 gram becomes equal to 6.02 into 10 to the power 23 U. That means 1 gram, the unit 1 gram is this number times the atomic mass unit. It's this number, which we call, which is a very, very famous number, which we call as the mole, or which is also called the Avogadro's number, is essentially the ratio between these two units, the relation between these two units. 1 gram is equal to so many times U, and it is called the mole. It's called the mole. It's also written by Na, like Na. Sometimes people write it as N, or sometimes they write it as A also. But it's just a sufficiently large number. But it's a very convenient number. It's a very good number to have because it makes life very simple. Because this number is the ratio of these two units. A very convenient practical unit like gram, and a very real unit of atoms in which we actually measure atoms and molecules. So 1 gram is Na times U, 1 U, and Na is the ratio of these two units. This Avogadro's number is a ratio of two units, exactly the way we have these. It's a unit multiplying number. A scaling number. I mean, a number which scales units. For example, when you say a dozen, it means 1 dozen of anything is 12 times that thing. So any unit, 1 dozen gram will be 12 grams. Similarly, kilo is 1,000 times. So kilometer is 1,000 times a meter. Kilogram is 1,000 times grams. So kilo, the word kilo is 1,000 times. Dozen is 12 times. So 1 mole is 6.02 into 10 to the power 3 times. That's all. It's just a unit magnifying number. And it's very useful because it helps change atomic mass unit into grams. So this is what this slide is saying. Dozen is this, kilo is this, mole is this. And therefore, if you have this equation where you have everything written in atomic mass unit, you know the weights of individual atoms and individual molecules, you multiply the whole equation by mole, by this unit magnifying number. So you get this, like you have 56U multiplied by Na. That means you take Na of all these things, of Na number of reactants, Na number of reactants, and therefore you will get any number of products also. But see, because it's U into Na, U times Na gives you a gram, the whole equation gets converted into grams. The number chosen, this Na, Avogadro number, is so smartly chosen that it simply turns everything into grams. And that's why when you write the mole, you write atomic number in grams, or molecular number in grams, molecular weight in grams. That's it. There's nothing, no big deal. But the point is, it makes life so simple. Firstly, we have practically measurable quantities. Now you have 56 grams of iron, 159.5 grams of copper sulfate. Very practical. And also, so that's why we take mole. I mean, from this equation, instead of 56 U of iron, we take 1 mole of iron, which means 56 grams of iron we take. We take 159.5 grams of copper sulfate, and we get so many products. So that way, you know, just by taking the correct number, chemists have solved this whole problem of converting atomic weights and molecular weights into practical units, but also the whole problem of numbers and masses. Both have been solved. See, I'm saying chemistry folks are smart. This was indeed a very smart step. So elegant, so beautiful. Find the correct number, multiply, and everything gets converted into grams. So all atomic weights converted into gram atomic weights. One master stroke. So life becomes simple. And this, I mean, this is for students, but molar mass of C would be, what would be molar mass of C?
12 grams.
Yes, 12 grams. Molar mass of oxygen, O2?
32 grams.
32 grams. I mean, the atomic weight, the molecular weight. Just write it in grams, that's all. And life is simple. So essentially, firstly, solve the practical problem of weighing, and then we know the exact number of particles there. So it's not only that the measuring of reactants has become easy. We know how many particles are there, and we are ensuring that equal number of particles are there. If you take 1 mole of each substances, or I mean the correct moles of each substance, you are ensuring. So why does the mole become important in chemistry? You tell me.
It simply converts mass into particles.
Yes. And but why are particles important in chemistry?
To carry the reactions without wastage using the correct proper amount of reactants.
Yes, the reactants actually are meeting each other in particle to particle. Reaction is happening between particles, not masses. It's each atom, and each atom is interacting with some other atom or some other atoms. So it's particles which are reacting. And these particles have different masses. So we have to solve the problem of masses. We have to solve the problem of particles. So just by inventing
Chemists they are counting while weighing.
Yes. So chemists are counting while weighing. Yes, just by inventing this one smart number. So so these are the reasons why we use mole, because we know the number of particles. We can take equal number of particles, and we have convenient units, mass units. So now the same reaction we will do equal in mass, equal in volume, and now this time we will take equal number of moles also of the same reaction, the one which I was showing you earlier, copper sulfate and iron. Manisha, will you show?
Yes, ma'am.
So I'm stopping sharing, and Manisha will show when we have taken all the three in 3 test tubes or 3 beakers. This time we'll do comparatively. So Manisha, you can switch off the volume because I will give the commentary. We are just showing you that we have taken 3 beakers, and when we say W, we have taken equal weights. So 0.5 gram of each of the 2 reactants here. And then when we say equal volumes, we have taken just 1 small spoon of each here. And here, when we say equal moles, we have taken actually 1/100th of a mole, because 1 mole is very large. 1 mole was 56 grams. So we have taken 1/100 of a mole. So 0.56 grams here, and 1/100th here, 1.599 grams. So when one thing you notice is that when you take equal moles, just see that the copper sulfate quantity is much larger in real terms. In grams, it's nearly thrice that much of iron. Here you took iron and copper sulfate equally, either in volume or equal in weight. But when you take equal moles, you have to take much larger quantity of Manisha. Manisha reached the other video actually. She'll just get back. But to take equal moles, when you calculate their equal moles, so the copper sulfate was 156 grams and iron was 59 grams. So copper sulfate was nearly 3 times as much in actual quantity. And then the reaction, we'll do it. And which Manisha is showing. Manisha, should I show? No, okay, Manisha is showing. थोड़ा आगे बढ़ा देना. So actually, now we are putting some distilled water. Actually, this is RO water, and a little bit of heating actually helps this reaction. I mean, like if it's very cold, then the reaction doesn't happen well. Also, we've had some trouble with this experiment simply because we don't have fresh iron powder. Our iron powder gets old, so some of it would be oxidized. But even then, we do with all the 3 of these. And then we see the results. We actually heat it a little and then see the results. So, Manisha, you can show the, yes, here we are seeing the results. Manisha, can you make it full screen? I mean, so you can see the results here in where you have equal weight, then you have equal volume. So if you see the equal volume and equal weight, a lot of iron seems to be left unreacted. I mean, you can test it with a magnet and see that a lot of iron is moving here. So clearly the iron was more than needed. And same with the other one, which with equal weight, there also if you test, so we have written W here. So you see, if you test again here, you will see the iron was more than required. Actually, the copper sulfate should have been more. We do see that copper sulfate has been consumed, but much of iron is left. So that, then now we will see the equal mole one. And actually, you can keep a solution of copper sulfate nearby to compare colors. So here's the equal mole one. And if you see clearly here, firstly, I mean, if you run the magnet, still some iron is left. Actually, reaction doesn't reach completion even when we do, because probably, I suspect that some of our iron is oxidized or for whatever reason, but you can see a lot of copper here now. Instead of black color, you can see the brown color of copper. And also the original color of copper sulfate is nearly completely converted to the green color of ferrous sulfate. So the color conversion also shows you that the reaction has reached far more completion. And also the color of copper powder also shows that much better result has been achieved when you took equal moles. So it's good to compare the color with original color of copper sulfate. So that's what we wanted to show you. Thank you, Manisha. So that way, I mean, we have actually sort of proved experimentally that taking equal number of moles is a better idea. So this is what we were doing. We had taken this much, and I mean, the same thing shown on slides actually. And how do we judge if the reaction is complete or not? You tell me. What are the ways you can judge?
From the quantity of iron left using the magnet you have shown, ma'am.
Yes. So one is by checking with magnet. What else will show us? Color. Yeah, so change in color. Change in color of what all?
This copper sulfate converted into ferrous sulfate, that color change from blue to green.
Yeah, so we should get more of blue to green color. I mean, more of green color, and also similarly gray to brown. Yes, yes, thank you. That's what we are saying here. So the color of reactants, both reactants, the color of both products, and also the presence of iron shown by magnet. This reaction is good because all these indicators are there for us to see. So, so deliberately chosen this one, and the same thing shown here. I mean, here, so we have done this often. So this is another iteration where the same thing is shown. So you can actually see these 4 test tubes. This is the original copper sulfate color. Here, copper sulfate is converted, but not fully converted. But in this one, where M is written, you can see the green color is the maximum, and also the copper retrieved, taken out, is much more. So, I mean, the same thing being asked here. So now can we explain this result, that we get the best result in when we take equimolar solutions? So why this result now? Can I show the flask which we heated? Yes, yes, of course. Manisha will show. Manisha, that flask. Actually, we heated all the 3 flasks. Because without heating, the reaction doesn't happen very well, especially in cold climate. So we heated all the 3, but the third one, the one with M written, has equal moles.
Since it has equal number of particles, so reactor
yes, exactly. Exactly. So as ma'am said, since the number of particles in the mole one is equal, that's why the reaction is the best in that case. So, is this fine? The person who wanted to see the beaker? Okay, a third. Yes, okay. So yeah, thanks, Manisha. So we have ensured, by taking equal moles, we have ensured that we took equal number of particles of the reactants, and therefore the reaction is happening the best. So, I mean, well, asking so many questions is normally done with children, because for them it's a very new idea. So it takes time for them to absorb. I mean, since you are teachers, I can go faster. Like many of you know this already, but I'm, like I said earlier, I'm trying to show you a pedagogy, how you can teach it also. How you can make this idea clearer to children. Is there any question anyone wants to ask? Before I proceed?
Yes, one question. So this reaction is chosen perfectly because you could see both the reactants and the products. So do you have any other suggestions of, similar reaction? Because there is some iron left over, and as you know, children, they will be the first to point out that the iron is left over.
Correct. But actually, we had a hard time thinking, because we did not want any reaction in which gases are involved, because they anyway are invisible, difficult to collect, and so many complications. So there shouldn't be any gas. So solids and liquids. And then even in solids and liquids, it has to be color change, and both reactants should be visible, both products should be visible. So there are not very many reactions where all these conditions are actually met. So, and there's color change of both. So that's why, I mean, I'll have to think, maybe, I mean, like, you are all chemists here, maybe some other reaction you can suggest that will help us also. We'll have to think about it. I mean, which reaction will have solid and liquid, solid or liquid reactants, both having different colors, and then the products should also be different colors.
Yeah, this was beautiful, but this was very nice.
Ma'am,
Yeah.
it's a good class. But one question is that all these reactions follow the law of conservation of mass.
Yes, of course.
Then when you wrote the chemical formula of that reaction, the weight of ferrous sulfate and the product weight is different entirely.
Okay, let me just see. I mean, it shouldn't happen because let me just get back to my equation.
No, ma'am, the atomic weight, it was equal in both sides. 56 plus 159.5 equals to 152 plus 63.5. It is 215.5. It is equal only.
Yeah, it has to be equal. It cannot be anything else because it's the same atoms going from one place to another.
But in copper sulfate, it is 159.5 U. Then ferrous sulfate, it is 1.2 U.
See, it's like, see, I had earlier given weights of each of these separately, no? I mean, let me just get back there. Where I have given individual weights of each of these. Wait, I mean, let me, where I must, wait, I'll just look for that slide where individual weights are written. So actually, I mean, like weight of copper, weight of sulfur, weight of oxygen, all these will have to be taken, atomic weights of each. And like one of them is with 0.5 because of that, it's taken as average of isotopes, no? I mean, that's how we take. So,
actually, copper weight is 63.5. It is higher than iron. Iron is 56. That's why it is getting more when it is converted into FeSO4. And copper sulfate, it is 159.5.
But law says that a mass is neither be created nor be destroyed.
Ma'am, sir, actually total number of reactants, that is equal to the number of
that's all,
products.
That's all. But that law follows a mass is neither be created nor be destroyed. It is before reaction or after reaction.
So basically the total mass before reaction, total mass of all reactants summed up together will remain the same as the total mass of all products summed up together, not individuals. It's not about individual masses. The law of conservation of mass says that total will be the same before and after, which is the same here.
Okay. Thank you.
All right. Okay, so is there any other question before I proceed? Because I want to get to gases also.
Fine, ma'am, you can proceed.
Yeah. So actually, I have lost my wait, my slide. Which slide I was on? Manisha, मुझको बता सकती क्या? Which slide I was on? So I'm just reiterating the same thing, what I said earlier. Okay, somebody has asked water of crystallization. See, when copper sulfate, this crystalline form is formed, it is definitely added with water of crystallization. But here in this reaction, it won't matter because when you dissolve it in water, when you dissolve copper sulfate in water, actually water of crystallization will mix with the rest of the water. The water of crystallization will go away. You will all have copper ions and sulfate ions actually floating freely. So here, that water of crystallization will not be added to the weight. So Shobhana is saying, is there a possibility of a recorded version? Yes, it's actually live on YouTube. It will be stored on YouTube. So Manisha will just post the link channel, the link of our channel where this session is there stored, but many others are there. Some are Hindi, some are English, so you can always look at it. And also we are trying that many concepts, we make short videos. Currently they are in Hindi. We are trying to make them in English also. So mole concept is also available in Hindi as a short video. So Manisha will also post the link of that channel. So, and we try that we help teachers with concepts, how to teach those concepts. We try to make them simple. So, Manisha will post those, both the links there. So, okay, I have to share my screen. So once again, repeating the same thing, that if we take moles in chemical reactions, number of particles is known. We know how many particles are there. It's also correctly taken. So, I mean, all reactants can be taken in the required number of, like equal number of particles. Then masses can also be measured in convenient units of grams. And then our reactions go to full completion without excess amounts of reactants, and there's no wastage. So there are so many advantages of taking the mole. And then I'm just showing you a lot of terms which are used for the mole. Basically, they all mean the same. When they say gram atomic mass, gram atomic weight, gram formula mass, molar weight, molar mass. Actually, I don't know why so many confusing terms are used, but they are saying the same thing. The total mass in of whatever particle you are talking about, so it's taken in atomic units, and then it is written in grams. So Manisha has posted the link of the short video channel. She'll also post the link of she has posted the link of live sessions also. You can save that. Here, there's a tool for conversion. I mean, if you want to convert something to moles or from moles to number of particles, etc. I mean, this is kind of, I found this trick in some book, and I found it useful. Do you want me to tell you? So often you're required to convert from here to here, from units to particles to moles to grams. So you want me to tell you that? So here, so this is given in a book. This was given in a book, so I liked it. So you create a conversion factor. I'll tell you how to create it. You make a conversion factor. How you create, the numerator and denominator should be 1. The two quantities, the quantity that you put in the numerator and the quantity you put in the denominator should be equal, so that this upon this should become 1. And in the numerator, you put the quantity which has been asked in the question. I mean, the question will ask, suppose the question asks you number of particles, then put number of particles in the numerator, put it above. So here's an example. Suppose, I mean, conversion factor, 2 conversion factors are shown. For example, 1 mole of hydrogen gas. Hydrogen gas is H2. So when 1 mole of hydrogen gas is put in the numerator, the denominator is 2 grams. So the numerator upon denominator would be 1. Both these quantities are equal, so this will be 1. Or you can put the reverse also. You can put 2 grams above and 1 mole of hydrogen gas below, and the conversion factor would be 1. Depending on the need, what do you need in the numerical, you can take either of these, whichever quantity. So the quantity that you need to calculate, put it in the numerator. So here's an example. Suppose you are asked, the numerical asks you, find the number of particles in 8 grams of CO2. This is the question, suppose. So since you want number of particles, you will put so you will create a conversion factor. So the conversion factor is Na particles, number of particles. We know that Na particles, which means Avogadro's number of particles, are there in 1 mole of carbon dioxide. So we put Na particles here divided by 44 grams, which is 1 mole of carbon dioxide. So Na upon 44 grams equal to 1. So this is your conversion factor. And now you want to find in 8 grams. So simply multiply 8 grams with this conversion factor. So it becomes 8 upon 44, which is 0.18 times Na. I mean, you can take the actual value of Na, which is 6.02 into 10 power 23, and you get the final answer. You get how this works? Just create this factor. One quantity divided by another quantity. Both the quantities should be actually equal in terms of, I mean, basically molar quantities. And put that one which you want to calculate. Since it is asking you, the question is asking you fine number of particles. So that's why particles have been put on top. And the other quantity, 44 grams, is put on the denominator. Nothing much to it, but I mean, I thought it was something helpful. So I put it here. Shall I move? I mean, if this is clear, then I'll move. I want to get to gases. I mean, this conversion factor thing, is it clear, or I mean, I need to repeat?
Yes,
Okay, move on.
All right. So suppose we have a reaction of two gases, which is hydrogen and oxygen. I've taken a simple example. So this is H2 plus 2O2 gives us 2H2O. So actually, now it's not only one mole and 1 mole, it's 1 mole of hydrogen with 2 moles of oxygen gives 2 moles of H2O. So Shobna has asked 6.023 into 10 to the power 23. Yes. I mean, if you want to go to the third decimal place, then of course it's 6.023. Otherwise, we take 6.02. That's actually depends on how much accuracy you want. So the thing is, for gases, actually weighing in real reactions, in real chemical reactions, weighing gases is very troublesome. So instead, volumes are far easily measured. I mean, because you have bottles of fixed volumes. So in gases, it's good if we can know the volumes, like what volume will contain how many particles. If we knew that, it makes life simpler. So here we know that like 1 mole of H2 would be 2 grams. We know it in terms of weights, but we don't know it in terms of volumes. Weights are known here, but so for gases, if we want to connect weight and volume, we have another law helping us. So which was actually given by Avogadro himself. Avogadro, you can see, was born in 1776, and from this period he lived. In this period, actually, if you see, that full atomic theory was also not developed. So the Avogadro number, the number that we use today, was not given by Avogadro. It's only named in his honor. That number came much later, when atomic weights were measured and so many experiments were done with atoms and molecules. Then the number came much later, but it's called Avogadro's number because he's honored because he gave us this law, that under the same conditions of temperature and pressure, equal volumes of different gases contain an equal number of particles. So what he's saying is that if you have two gases and you take their equal volumes, then you have equal number of particles. And I mean, wait. And he actually made this law with the assumption that actually the particles, gas particles, are too small and there are very large spaces inside gas, the ideal gas assumption. So actually particles are so far away and there's so much space inside that the size of the particle here doesn't matter. In the case of gases, the total volume of gas is not affected by the size of the particle. That was one assumption. And the second assumption was that particles are actually barely interacting with each other. They are so far away that they don't actually attract or repel each other. So these are ideal gas assumptions. So with these ideal gas assumptions, if two gases are occupying the same volume, they will have equal number of particles. So, and we already know that 1 mole of all gases will have the Avogadro number of particles. That has been told to us by atomic theory. So basically, we get to know that each mole of a gas, any gas, 1 mole of any gas occupies a fixed volume. So this is like this volume that at STP, 0 degree C and 1 atmospheric pressure, 1 mole of any gas occupies 22.4 liters. So that volume is known. So for every mole of any gas, volume is known. So that helps us, find from reactions, chemical reactions, it helps us find volumes also, or predict volumes. How much volume of one gas should I react with how much volume of another gas, and how much volume of the third gas I'll get. So it's like you have chemical reactions in terms of volumes now. First you had it in terms of weights. Now you can, using this relationship, it holds for most real gases. So unless they are very high pressure, then we calculate volumes at 0 degree and 0 degree centigrade and 1 atmospheric pressure, and then using the ideal gas P1 V1 upon T1 equal to P2 V2 over T2, you can find the volume at another temperature. If you have at 0 degree temperature, you get it, the volume, then you can calculate using this at any temperature, suppose 30 degree or 40 degree, any temperature that you have in your room, then it can be, the volume can be calculated from this. And of course, the ideal gas law also gives us PV equal to nRT, where n is number of moles. So we have number of moles helping us here in volumes also, finding volumes of gases or making gases react, and converting reactions or handling reactions of gases. So that's how moles becomes very useful in weighing reactants or measuring their volumes in terms of gases. So it helps us across board, makes life extremely simple. It's terrifying. Mole is scary simply because it's never explained properly. Rarely I have seen it being explained properly. Nobody knows, most people don't know that it's a ratio of two units. It's nothing else but a ratio of 2 units. You just see the relationship between gram and atomic mass unit, just divide and you get the mole. So actually, this is all I have for today. But if you have any questions, I'll be happy to answer.
Madam, one question. Yeah. This is Shobna here. I joined the session halfway through, so I really didn't know what happened earlier. But then when you were explaining about finding the moles of gas at standard temperature and pressure, I would like to know if you have any other experiments to show that we could replicate in the lab, because again, collecting gas is not so easy. We have a good lab in our school, but then I haven't been able to show them in terms of mole, how I can explain it with an experiment. So is there any way that you can suggest to us a lab that we can show children?
See, I mean, actually, in this session, since you didn't see the first part, we used an experiment with liquids and solids to first explain what mole is. So mole is and where it came from. So, and how it helps us in chemistry make sense of, I mean, actual reactions. I mean, when you have to actually measure reactants and products and all that, and yeah. I mean, you take the best quantity of reactants so that your reactions proceed the best. So for that mole is used. So I don't know whether you saw that part, but here, this second part, I was just mentioning that the same thing can be used for gases simply because of that relation which Avogadro gave us. Without that relation, you will not be able to prove it.
Correct.
That, yeah. So I'm saying that, I mean, like 1 mole actually occupies 22.4 liters.
Right.
That you won't be able to actually show.
Right. So I just wanted to know if there is any, if there is any suggestion from your side where we can actually show the volume of gases produced with the help of a simple experiment. We could, in fact, we have done it through a release of carbon dioxide, for example. We have found out with an experiment where we can say, after the gas is released, if you could collect carbon dioxide gas, and then if we found the volume of that gas, so we could say, and related to what would have happened if you took 1 mole of that gas, then it should be 22.4 liters. So I'm asking if there is any way that you can kind of tell us a simple lab where it would be helpful for us to measure the quantity of gas released, and then we could equate it with the mole concept.
I don't see it being simple. I mean, not that we have tried also. We'll have to think more about it because there's one difficulty here. See, temperature is easy to measure. I mean, you collect a gas, let's say, in by downward displacement of water, right?
Right. Right.
Now, if any, there at least you can assume that the atmospheric pressure, the pressure is atmospheric pressure, right? So you know the pressure, and temperature is your ambient temperature. So you know temperature and
standard
pressure.
Room temperature. Yes.
Yes, a standard room temperature, and you have the volume by actual measurement. I mean, so there. But if any extra gas goes more than your bottle, then your pressure inside will increase.
Yeah.
And then you'll have a problem. So you have to be careful that you do not fill your full bottle.
Right. Right.
If you don't fill it, then you can make that relationship. Then you can measure the actual volume and temperature and pressure, and then from that you can actually calculate the amount number of moles produced. So it's the other way around. You will be using
and what?
If you try weighing it, I mean, with very sensitive balances, maybe you may be able to weigh that gas. Then your bottle, which is bottle's weight without air, you should know, which is again difficult.
Yeah.
So that's
what about using syringes?
Even so, the problem is that you have to know. If you want to weigh the gas, see, to actually prove this, you have to weigh the gas. Now, how do you weigh the gas unless you know the weight of the container without air? How will you do that? I mean,
all we need is volume, right? Don't you think all we need is volume? If you have the measured volume, say for example, syringes will have those measurements.
No, the volume is
right.
easy.
So
weight of a gas is more difficult, but probably what you can do, I mean, I'm thinking now, maybe you can fill your bottle with water, weigh it, so that, and subtract the weight of the water, the volume, I mean, you know the volume of the water. So subtract the weight of the water to get the weight of your bottle without air. but you are likely to
Right.
get into errors in this because
Right.
there are many sources of errors. The weight of the gas is very tiny.
Right.
In comparison, the weight of water,
Correct.
weight of bottle, everything is much more. And sources of error are
Okay.
also very many. So I suspect
Correct.
that you will not land up with very good results. So that's
Okay.
more of a worry than.
Okay.
So actually, you see, whenever such things are proven, what Avogadro proved, very sensitive equipment with far amount of care, lots of care and all that will give these relationships. So I suspect that you'll have to be
Right.
very careful. You can give it as
Sure.
a challenge to children. I mean,
Yeah.
prove Avogadro's relationship.
Theory. Yeah.
Madam, that is why it is
Yeah. So
termed as
one
concept. More, it is termed as small concept. Concept means it is an idea only. That is why.
Right.
That is why these complications are there. That is why the mole concept is named.
I didn't quite get your question.
Yeah, a
See,
lot of
all concepts
it
are ideas.
The previous one asked about the gases of the experiment shown in the lab. It is very difficult because it is concerned with the gases and everything. That is why that heading is termed as concept, mole concept.
No, concept is a word used for any idea which we make which has a definition which actually relates to other ideas. Concept. See, even animal. The word animal is a concept. The word man is a concept. So concept is a very general term used for anything which we utilize to describe something in our world. So I don't know why you are confused with the use of the concept. If you want, you can just say the mole. The idea of mole.
I tell it because the concept means it's a fantasy.
No.
Because
concept,
we cannot see the particle, we cannot touch the particle.
Okay.
We can only see it in shape. That is why I call it as fantasy.
No, there is no fantasy here. Can you touch your country? Can you see your country? So it's a concept. Country is a concept. So is it fantasy? Will you call it fantasy? Man is a concept.
Yes.
You can touch a single man.
At the same time, man is lively.
Sorry?
Lively. Man is lively.
Man is living, that's true.
Yeah.
But I'm saying there are so many concepts we talk about which are not right there, which are not in concrete terms in front of you. I just gave the example of country. I can give you 1,000 other examples which you use every day. Religion, what song, I mean, poem, letter. All these are concepts. So they are not fantasy. It's just that word describes something which has some meanings in our minds, and we use that word to share that meaning. That's all.
But then why mole is always as a headache to the students and also teachers every time?
It's a headache because it's not explained properly in textbooks.
And we cannot practicalize it. That is the main thing.
Why?
Yes, ma'am. I also feel like that. See, in practical, you can with only solids, not with gases. What he is saying is correct only.
No, with gases, I see the problem. But but we practically measure 1 mole. We practically measure half mole. Why can't we practically measure make it practical?
In terms of ideal condition.
No. I mean, see, you can. We were weighing one mole of iron. We were weighing 1 mole of copper.
That is solid. In case of hydrogen, how can we prove it as ideal? Ideal gas of hydrogen?
Oh, that you are saying. See, the thing is, it's like real gases actually at low temperatures and pressures, they behave as ideal gases. And that approximation has to be made, otherwise you will not be able to deal with gases. Such approximations are made in science all the time, in all sciences. So we measure things only by approximations, otherwise you can measure nothing.
It is an assumption, madam. It is an assumption.
It's not an assumption, it's an approximation.
There's
a difference between assumption and approximation.
Is it proved?
Yes, yes. That real gases behave as ideal gases. This is, of course, scientists would prove it. Why? Otherwise, they will not even ask you to do it. See, scientists' job is not only to convince you and I. They have to actually, their whatever theory they give, they have huge amount of applications. I mean, think of industry producing gases in thousands of tons. If scientists did not give the correct theory, there'll be huge amount of errors. It will, the whole industry producing gases will go haywire. So scientists have to give correct theory. I mean, if they say real gases behave quite close to ideal gases, they mean it.
My question is that, considering physics and biology, chemistry has always changing every time. In case of atom, the structure of atom is considered as a solar system. Then it is entirely different in another term. Next class, we studied about the atom is just like a cloud, a positive and negative.
Increasing complexity with different levels of character.
Then students asked us, you are not stable chemistry teachers and chemistry is not stable like physics and biology?
See, if you started with atomic orbitals, students would run away. They will never even enter into chemistry. But that trouble is there. I mean, ideas getting complex is true with all subjects. In all subjects, as you move towards +2 and as you move towards graduation, ideas get more and more complex. It happens in physics also. It happens in biology also. I mean, it's not only a problem of chemistry. I mean, I understand that as teachers, we have to struggle with all this, but there's no other choice. How can you introduce very, very complex concepts to young children?
Especially
They'll not understand anything.
Especially in studying more concepts, every corner students are asking about complicated questions about this. How can